My name is Bergen, and I will be presenting the solution to the problem ISP Merger in BGOpen 2018. So the problem is, we're given a graph, we're given some degree constraint, which limits the maximum degree each vertex can have, and we're given a budget, K, for how many edge additions or deletions we can do. And we want to answer yes if we can connect the entire graph satisfying the degree constraint, or no if it's impossible. So the first thing we have to realize here is that we don't really care about how each connected component in our graph looks on the inside. We only really care about how many free connections points. So here we can connect one additional edge to this vertex without violating the degree constraint. And we also care about how many additional edges this component has, which can be deleted. The first step is going to be to classify all the connected components. So when I say classify connected components, I mean that we're gonna map every connected component to a tuple of two values, which is going to be the component free and the component non-cut edges. So if we label these components as A, B, and C, for A here, you can see that we have exactly one free. For B here, we have 0 free, and C, we have 1 free. For non-cut edges, only A has a non-cut edge. We can find the non-cut edges by just looking at the minimum number of edges in a tree with the same number of vertices. Every edge after that is a non-cut edge. So now we have a classification of the connected components. For every component which is 0, 0, is a tree without connection spots. So to connect this to anything else, we have to split it up. So we're gonna, for every one like this, we're gonna create a component like this and this. No matter which edge we delete in B, we're gonna get two components like this. So now we have some number of components. For this instance, it's going to be these 4. Now you want to connect them together. The optimal way is to select the two components with the most connectivity, connect them together, and maybe delete some edges if we have to. So what I mean by connectivity is that we're going to order by the number of free slots first. This is the most important sorting, except for any components which have no non-cut edges and only one free spot. These are going to be ordered last. Then we sort by number of free spots, and we can tie break on total edges. So to do this efficiently, we want to create a priority queue. We put all components into this priority queue. So now we're going to go into a loop, which we continue until we have either only one component or we have exceeded our budget. We can label them C1, C2. So for both C1 and C2, we need some free connection spot. So in the first iteration here, we're going to take these two. These are the first one in our priority queue. Both these have free connection spots, which is fine, and we can just add them together. C1 and C2. So if we have some component here, C1, C2 is going to be a tuple of free and non-cut edges, and the same for here. We always get a new component, C prime, and it's going to be free from C1 plus free from C2. It's impossible to see, I'm sorry. -2. And the non-cut from C1 plus the non-cut of C2. So this is we don't have to know where we connect the edge, we just add this new component back into the priority queue. However, if C1 or C2 does not have free connection spots, if I have 0 free connection spots, then we need to free up some. So whenever we delete a cycle edge, we get 2 free connection spots, and we use 1K. We do this if needed. If we have one of these components is like this, then we know that either C1 or C2 has no free connection spots and we can't free up any space, then we can just answer no. Then we have a no instance. So now we have joined C1 and C2. So for this instance, we're going to get one component with 1 plus 1 minus 2 is 0, and 1 cycle edge. So where does this fit in our priority queue? Well, we want to order these one last anyway, all the time, so we're going to put it here. This is now our most connectable component, even though it has 0 free connection spots, and the other one has free connection spots. Because if you connect these two, then we create something which can't be connected to anything. So the next iteration, C1, C2 is going to be this 0, 1, and this 1, 0. So C1 can't be connected to anything because it has no free connection spots. But we have an extra non-cut edge which you can delete using one operation. So we do that, and we get 2 free connection spots here. Then we do the merge. So we get 2 plus 1 minus 2 is 1. And we add this component back into our priority queue. Finally, we only have these 2 left. We can just connect them. So this is how the algorithm solved this case, and it's going to be yes if k is 4, because we only used 4 operations. If k is 3, then we use too many operations, and we just answer no. This is the optimal algorithm for solving this, and it also then can just tell us if it's possible or if it's impossible.